The James Webb Space Telescope, JWST, is delivering on its promise to transform our understanding of the early universe by probing galaxies near the dawn of time. One of these exceptionally luminous galaxies existed when the universe was just a tiny fraction of its current age. This means the light left the source long before our Milky Way even formed. How amazing is that? However, as the earliest and most distant galaxies ever seen, it is also one of the most enigmatic. Why is it so bright? This question has exacerbated the ongoing crisis in cosmology. Join us as we dig deep into how James Webb's newest discovery has just shattered our understanding of the cosmos. Humans have long found meaning in the stars, but only recently have we begun to understand whole clusters of them, galaxies, way out in the depths of space. A few nearby galaxies, such as Andromeda, have always been visible to the naked eye as a dusky smear in the night sky. Other shimmery structures became known to us after the invention of the telescope in the 17th century, sparking a debate about their nature. Were they clouds of cosmic dust within our Milky Way or island universes of their own? Not until the 1920s did humanity identify these glowing clouds as galaxies when astronomer Edwin Hubble, relying on the work of lesser-known astronomer Henrietta Leavitt, found that some stars were too far away to belong to the Milky Way. Only in the mid-1990s, when a space telescope named for Hubble peeked farther into the universe than ever before, did we find thousands of galaxies shimmering across the universe, island after island in a vast cosmic sea. Astronomers felt confident that they understood galaxies and how nature makes them until startling developments arose, courtesy of a space telescope far more powerful than Hubble. The James Webb Space Telescope, in full operation since summer 2022, has shown that galaxies formed much sooner after the Big Bang than scientists previously thought, and that some are unexpectedly large and brimming with stars. These findings have thrown scientists into a new reality where their existing theories no longer apply. As Joel Leha, an astronomer at Penn State University, said, everyone in the astronomy community knew that the Webb telescope was going to be revolutionary, and we had a very clear list of things that we thought Webb would totally blow our socks off about. But the discovery of cosmically chunky galaxies where there shouldn't be any, this was nowhere on it. No one was looking for this. Those early results came quickly because researchers used a clever shortcut to estimate galactic distances. Astronomers usually pin down cosmic coordinates by precisely measuring redshift, a stretching of a galaxy's light toward the red end of the electromagnetic spectrum as a result of the universe's expansion. For example, a light bulb that emits pure violet light, if placed in a region of the cosmos roughly corresponding to a redshift of 1 as seen from Earth, would appear as deep red. By comparing the observed spectra from these galaxies with that of a source at rest, we can infer how fast the galaxies are receding from us and hence how far away they are. If all cosmic history is a book, the redshift acts as the page numbers indicating when something is happening in the story. Unfortunately, not all the chapters are visible to us. The cosmic dark ages make up the bulk of the book's missing pages. Imagine reading Shakespeare's Hamlet and skipping some initial scenes. You would transition from someone whispering in the darkness on the battlements of a castle in Denmark to a prince seeing ghosts and stabbing at tapestries. This is the situation that astronomers face. We now possess an excellent description of how it all started. The Big Bang theory has successfully explained the features of our universe. Just a few numbers called cosmological parameters can fully describe the universe's initial conditions, and decades of observations have confirmed with spectacular precision that cosmic history seems to have begun with a fiery expansion from a single, still mysterious, primordial point. But a shadow fell across the universe as matter cooled from its early incandescence and relatively simple initial conditions advanced into intricate complexity. This is the source of the rift in cosmic history, the darkness where astronomers wander. What's certain is that a few 100 million years after the Big Bang, a blink of an eye in cosmological terms, the Great Shadow began to lift. Enormous clouds of gas collapsed, and stars, perhaps hundreds of times heavier than our Sun, sparked a light, beginning a photonic deluge that over eons illuminated the universe. In this brief cosmic period, all the protagonists of our story, including black holes and galaxies, started to peek through from behind the dark curtain of the cosmic stage. The first stars were mostly made of hydrogen and helium, the lightest elements of the periodic table, as heavier elements did not yet exist. As they shined, these stars and their subsequent kin transmuted those light elements into heavier carbon, nitrogen, oxygen, and other elements crucial to the universe as we know it today. These elements, the ashes from early stars, eventually formed everything we observe around us, you and me included. To fully appreciate this milestone in our chronicle of cosmic history, we must fill in the missing pages surrounding it. How did the first stars, black holes, and galaxies form? How big were they? How fast did they grow? How was their evolution interconnected? How did the cosmic transition from simplicity to complexity lead to at least one world where curious creatures gaze up at the sky and wonder? Without such details from these few but fundamental chapters, our understanding of the universe and our place within it will be forever incomplete. This is the deepest, purest reason why astronomers seek sources farther and farther out. We are privileged to live in an era when telescopes of unprecedented power, like the James Webb Space Telescope, can aid us in this cosmic endeavor, acting like time machines. More distant galaxies have since been discovered by James Webb that are invisible to Hubble's capabilities. At the end of 2023, 9 of the top 10 most distant galaxies known are Webb galaxies, with GN Z11 being the sole confirmed galaxy not requiring either discovery or confirmation with James Webb. Observations in October 2023 and January 2024 revealed a galaxy from less than 300 million years after the Big Bang during a period known as cosmic dawn, called GS Z14.0. This collection of stars existed a mere 290 million years after the Big Bang. To put this in perspective, if the universe is 13.8 billion years old, we are observing the galaxy when the cosmos was only 2% of its current age. GS Z14.0 was discovered to have a redshift of 14.3, surpassing the 2022 record of a galaxy with a redshift of 13.2, corresponding to a formation age of about 325 million years after the Big Bang. Astronomers find the most interesting aspect of this observation to be not just the great distance involved, but the size and brightness of GS Z14.0. Webb measures the galaxy to be more than 1,600 light-years across, which is about 5 times more luminous than the previous most distant galaxy. George Rieker, an astronomer at the University of Arizona and former deputy director of Stewart Observatory, remarked that nobody dreamed there would be galaxies this bright at such a high redshift. According to NASA, the light we see from GS Z14.0 comes mostly from young stars, not from emission near a growing supermassive black hole. This amount of starlight implies the galaxy is several hundred million times the mass of the Sun. This raises the question of how nature could make such a bright, massive, and large galaxy in less than 300 million years. This new reality seemed, for a brief moment, to threaten astronomers' fundamental understanding of the entire cosmos. If the starting point looked like this, could the standard model of cosmology, our strongest theory about the origins and composition of the universe, be wrong? For many astronomers, the answer is simply yes, but others believe the crisis in cosmology is an exaggeration. There are many possible explanations for how astronomers might have gotten it wrong. Perhaps early stars formed far more efficiently than previously thought, through mechanisms that scientists hadn't considered before. Alison Kirkpatrick, an astronomer at the University of Kansas who studies galaxy evolution, wonders whether cosmic dust in these galaxies could be playing tricks on Webb, making stars appear older than they really are. Additionally, cosmic dust might have been different back then. Elsewhere, Evo Lab, an astronomer at Swinburne University of Technology, suspects that black holes could play a role. Black holes are among the most luminous objects in the universe when they feed on cosmic matter, which glows as it gets sucked in. If you dump a lot of gas into a black hole, it will start to outshine the entire galaxy. Such black holes could make early galaxies appear brighter and more star-filled. But none of these possibilities change the fact that the first island universes are not what we expected. Even accounting for some weird new phenomena, everything is too big and it's too big too soon. Investigating these questions will require more Webb observations, particularly those that yield more detailed measurements of starlight known as spectroscopy. Astronomers need more data to confirm that the most unusual galaxies they've found are the real deal and to understand their composition, which will help identify the conditions in which they formed. Researchers are currently in the thick of it, with fresh spectroscopic data expected this spring. The effort verges on soul-searching. Primordial starlight has never been so in demand, and astronomers and theorists, those who observe cosmic wonders and those who explain them, don't know exactly what they'll find once they are finished. It's probably going to be about 5 years until we've totally settled into our new universe as revealed by James Webb. In one sense, these new discoveries have injected drama and even anxiety into a field that was quite stable. It's incredible how the universe is so much weirder than we thought, as Erica Nelson, an astronomer at the University of Colorado at Boulder, said. But in another sense, it's just fun. It's the beginning of the universe, so it's really fun to think about this kind of stuff. In addition to peering deeply into the cosmos, NASA's James Webb Space Telescope is giving scientists their first detailed glimpse of supernovae from a time when our universe was just a small fraction of its current age. A team using Webb data has identified 10 times more supernovae in the early universe than were previously known. A few of the newfound exploding stars are the most distant examples of their type, including those used to measure the universe's expansion rate. To make these discoveries, the team analyzed imaging data obtained as part of the James Webb JES program. Webb is ideal for finding extremely distant supernovae because their light is stretched into longer wavelengths, a phenomenon known as cosmological redshift. Prior to Webb's launch, only a handful of supernovae had been found above a redshift of 2, corresponding to when the universe was only 3.3 billion years old, just 25% of its current age. The JES sample contains many supernovae that exploded even further in the past, when the universe was less than 2 billion years old. Previously, researchers used NASA's Hubble Space Telescope to view supernovae from when the universe was in the young adult stage. With JES, scientists are seeing supernovae from when the universe was in its teens or pre-teens. In the future, they hope to look back to the toddler or infant phase of the universe. To discover these supernovae, the team compared multiple images taken up to 1 year apart and looked for sources that disappeared or appeared in those images. These objects, which vary in observed brightness over time, are called transients, and supernovae are a type of transient. In all, the JES transient survey sample uncovered about 80 supernovae in a patch of sky only about the thickness of a grain of rice held at arm's length, according to teammate Justin Pearl, a NASA Einstein Fellow at the Space Telescope Science Institute in Baltimore, Maryland. This is really our first sample of what the high redshift universe looks like for transient science, Pearl said. We are trying to identify whether distant supernovae are fundamentally different from or very similar to those in our own galaxy. At the end of 2023, Pearl and other researchers at the Space Telescope Science Institute provided expert analysis to determine which transients were supernovae and which were not, as they often looked very similar. The team identified a number of high redshift supernovae, including the farthest one ever spectroscopically confirmed at a redshift of 3.6, which means its progenitor star exploded when the universe was only 1.8 billion years old. This particular supernova is a core-collapse type, an explosion of a massive star. Of particular interest to astrophysicists are Type Ia supernovae, which are so predictably bright that they are used to measure far-off cosmic distances and help calculate the universe's expansion rate. The team identified at least one Type Ia supernova at a redshift of 2.9, meaning the light from this explosion began traveling to us 11.5 billion years ago, when the universe was just 2.3 billion years old. The previous distance record for a spectroscopically confirmed Type Ia supernova was at a redshift of 1.95, when the universe was 3.4 billion years old. Analyzing this Type Ia supernova found at a redshift of 2.9, Pearl determined that its intrinsic brightness was as expected, showing no evidence that Type Ia brightness changes with redshift. This finding is crucial because if their brightness varied with redshift, they would not be reliable markers for measuring the universe's expansion rate. More data is needed, but for now, Type Ia supernova-based theories about the universe's expansion rate and its ultimate fate remain intact. Pearl presented his findings at the 244th meeting of the American Astronomical Society. The early universe was a very different place with extreme environments, and scientists expect to see ancient supernovae from stars with far fewer heavy chemical elements than stars like our Sun. Comparing these supernovae with those in the local universe will help astrophysicists understand star formation and supernova explosion mechanisms at these early times. Fellow Matthew Seibert of the Space Telescope Science Institute, leading the spectroscopic analysis of the Jade supernova, stated that they are opening a new window on the transient universe, expecting to find exciting and unexpected things. Elsewhere, using the James Webb Space Telescope, astronomers have discovered the richest menu of hydrocarbons ever seen in a planet-forming disk. This observation involved the protoplanetary disk around a tiny star and revealed the first detection of ethane outside the solar system. The discovery was made when Webb's MIRI instrument investigated the object ISO 147 as part of the Mid-Infrared Disk Survey, MINDS. ISO 147 is a young star located in the Chameleon I star-forming region, about 600 light-years away. Webb's observations imply that the protoplanetary disks of tiny stars are more efficient at forming smaller Earth-like planets than larger Jupiter-like gas giants. Since low-mass stars are more common in the Milky Way, there may be more terrestrial planets in our galaxy than previously suspected. The findings also show that the planet-birthing clouds of gas and dust surrounding tiny stars are built differently, at least chemically, from those around stars about the size of the Sun and larger. This different chemical composition suggests that rocky planets around these relatively small stars may have very different atmospheres than Earth. ISO 147's mass is just over 10% that of the Sun, and it is surrounded by a protoplanetary disk with carbon-rich chemistry, featuring 13 carbon-bearing molecules, including ethane and benzene, but with a low abundance of oxygen-bearing molecules. This composition is profoundly different from what we see in disks around solar-type stars, where oxygen-bearing molecules such as water and carbon dioxide dominate. The MINDS team thinks this shows that material is transported radially through the protoplanetary disk of ISO 147, impacting the bulk composition of any planets forming within the disk. This has implications for exoplanet hunting because stars are born when massive clouds of gas and dust collapse under their own gravity, leading to infant stars being surrounded by protoplanetary disks. The amount and distribution of material in these disks limit how many planets a star can host and their building blocks. James Webb's ISO 147 results indicate that this protoplanetary disk is better suited for birthing smaller rocky planets rather than larger gas giants. This finding that disks around very low-mass stars evolve differently has potential implications for finding rocky planets with Earth-like characteristics, though tiny stars could host planets that are Earth-like in some ways but radically different in others. As Thomas Henning, MINDS team leader and researcher at the Max Planck Institute for Astronomy, pointed out, the primary atmospheres of these planets will likely be dominated by hydrocarbon compounds rather than oxygen-rich gases like water and carbon dioxide. The faster and more efficient formation of rocky bodies in protoplanetary disks around less massive stars compared to more massive ones is currently not fully understood. It could be due to carbon enrichment in these disks or a depletion of oxygen. If carbon enrichment occurs, it might result from solid particles being stripped of their carbon content, releasing it as gas. These carbon-deprived particles would form planets with rocky bodies poor in carbon, but their atmospheres would be carbon-rich due to the excess carbon gas. Thus, rocky planets around tiny stars would be quite different from Earth. Research leader Adia Arabavi from the University of Groningen noted that these findings were made possible by the James Webb Space Telescope's unique position, about 1.6 million kilometers from Earth. This location allows Webb to detect emissions that are absorbed by Earth's atmosphere, providing insights previously unattainable. The team now plans to investigate more protoplanetary disks around low-mass stars to determine how common such carbon-rich terrestrial planet-forming regions are. While James Webb is revolutionizing many areas of astronomy, its predecessor, the Hubble Space Telescope, continues to operate despite showing signs of advanced age. Last month, Hubble entered protective safe mode after detecting anomalous readings from a gyroscope. With only 2 of its 6 gyroscopes functioning, NASA plans to shift Hubble into one gyroscope mode, saving the other healthy one for future use. This mode will slightly reduce scheduling efficiency and flexibility but will allow Hubble to continue its mission. The telescope has operated with fewer gyros before and is expected to keep functioning until the mid-2030s. Despite this, Hubble's end might come due to atmospheric drag, which could bring it down in a fiery re-entry. NASA has explored ways to prevent this, including a proposed plan to boost Hubble's orbit using a SpaceX Dragon mission, but nothing is currently planned. Hubble's continued operation, even in one gyroscope mode, demonstrates its resilience and the significant contributions it still makes to our understanding of the universe.